So let me start with the definition, and I mean, let me say the action of like I think this whole continuous theory has to say something with cryptology is that I mean we can use it to model so-called maps. And so let me give you like I think I gave a similar motivation at ERGS a year ago. Let me give you like one motivation and one application of understanding assembly maps. I mean that's many applications of assembly maps in topology, like if you study Jones or like the Borel conjecture, which are in some sense the most important questions in geometric topology. It all, I mean, can be translated through surgery into like study of assembly maps in K theory or like A theory, ordinary grid theory. And so today is going to be we can give a reasonable model of assembly maps or like the easiest kind of assembly maps. And let me start like a little bit about this man and West like sort of theorems, like what they have to do with assembly maps. And I want to make a first definition. Simple anima, or like simple, I guess in more classical language, is a compact anima. Anima. That together with a lift of a certain class. So there's the A theory of Z. What is the A theory of Z? It's the K theory. And this is like non-continuous classical K theory of the category parameterized spectra over Z. And I guess now I have to take compact objects. I could write continuous K theory spectra to the Z. And I mean, usually people maybe write this more classically. If Z is connected, you can write it as adjoint omega Z. Which is a strictly worse description because it doesn't show all the reality, but maybe strictly better for talk. So anyway, so we have A of Z, and the point is, if this is a compact anima, this has a canonical object, the class, the object characteristic, or and that class is just given by, I mean, it's the class of the sphere, right? The constant sphere, parameterized spectrum over Z. The compact object by the assumption that Z is compact. And so this gives you a class, and really, I mean, I write X, and this is the spectrum, so I write points in the spectrum by meaning points in the underlying infinite loop space, or equivalently maps from the sphere. So there is this class, and then this guy, this A of Z, is obviously covariantly functorial in Z. So if you think a little bit about it, this is covariantly functorial because of the W, or if you want to think of it in terms of large categories, whenever you have a map from Z to Z prime, you get a strongly continuous functor from spectra Z to spectra Z prime, not the other way around. This is like why it's covariantly functorial, and then here you have this kind of assembly map, A of a point, which is just K of the sphere, and here you have the Z. And here's some sort of assembly map. Right, this is kind of the universal sort of transformation from this colimit, putting the colimit inside. This is like what an assembly map is. And so I want to pick such a lift here. And that's the definition. So simple anima is just such a compact anima. As a result, every compact anima has such a class, and I'm lifting it through this assembly map. That's what I mean. And in some sense, like you want to think of simple anima as some sort of thing, I mean, some sort of gadget, some sort of space where not only do they have like an Euler characteristic, but they have a local formula to compute the Euler characteristic. So this is like similar to, like formulas in differential geometry, where you somehow can compute the Euler characteristic of a manifold by means as the integral over like the Euler class. It's kind of a homotopy theoretic version of such a refinement. That's the definition. And I guess, in some sense, why is this a justified definition? I mean, like, after all, maybe you know a little about simple homotopy theory, and I mean, this is because of the following theorems. So let me list them. I mean, there's the first theorem by Wall. What does it say? It says a compact anima is finite. Right, so compact anima means retract of a finite CW complex, and finite means finite CW complex, if and only if
if it refines to a simple anima. Right, so when you start with such a sort of compact anima, you can exactly find this lift if and only if it's a finite anima. It's like maybe a modern formulation of what is reside. But
I'm sure Wall didn't formulate it this way.
Wall's an infinite group point.
you know, like Wall does actually takes a cofiber of this and replaces the sphere by the integers. So in the range of degrees where we care, the sphere, like k of the sphere is the same as k of the integers, and then you just like so the Wall finiteness obstruction is exactly the map from this into the cofiber, and you can lift exactly if this dies in the cofiber. That's exactly the Wall finiteness obstruction. And the next theorem is Whitehead. And that's in the 50, so even earlier than Wall. And he proves the homotopy equivalence between finite CW complexes. Or say from finite CW complex to itself is simple. Simple in the classical sense. What does simple mean? I.e. the homotopic to a proposition of elementary expansion and collapse maps. So an elementary expansion is where you attach a simplex along a horn, or like a sphere along half of its boundary. And that inclusion is obviously a homotopy equivalent, and a collapse is just the inverse to that homotopy equivalence. And so Whitehead tried to study like a combinatorial version of homotopy theory. But he tried to understand like which like homotopy equivalences are somehow witnessed in a finite like number of steps, in understandable steps. That's kind of the notion of simple homotopy equivalence, and I mean the statement is if and only if it refines to, I guess I should say a map in anima simple. Maybe I actually only give you the definition here. Should have maybe said how this becomes itself like an infinity group. And I guess how do you do that? So you just have like, you define an infinity groupoid, anima simple, which sits over the groupoid core of like compact anima, right, by definition, and somehow you find this to be a fibration, and it's classified by somehow the functor which assigns to like an anima and a invertible maps, the space of lift of the anima of lifts, that chi log of chi. Right, so this is just somehow how you make this canonically, and you might actually a priori think you can make an infinity category of simple anima, and that's, I mean, in some sense not possible, because if you think about this functor, the Euler characteristic as an object in A of z, this is only functorial like in homotopy equivalences, or slightly weaker maybe homology equivalences, but it's not functorial in arbitrary maps of topological spaces. The sphere will not push forward to the sphere unless you're a homotopy equivalence. But that's the point. So why you cannot make an infinity category of simple anima, but I can at least make a classifying anima, a space or infinity groupoid of simple anima, and that's kind of the definition. And then, I mean, Whitehead theorem can be recast in saying that if I give you an anima, it comes with such a sort of simple structure, then an equivalence, a homotopy equivalence, refines to a map in simple anima if and only if it refines to a simple map, or it is a simple homotopy equivalence. That's one way of stating Whitehead theorem. And maybe I should say, maybe just a statement about pi naught and pi 1 of this like space of simple anima. And I mean, you can actually make a more general statement, and that's maybe a theorem of. It's a little bit hard to attribute. If we say Hatcher, Waldhausen, and then Waldhausen, Jan Rockness. And let's say this space this, let me say, infinity groupoid, anima simple, is equivalent to, I guess, other spaces of simple animas, to, for example, Hatcher's classifying space of simple homotopy equivalences, simple homotopy types. And maybe they also give a very combinatorial model. What you can do is you can just take like polyhedra, the one category is polyhedra, and simple maps. So simple maps are basically maps whose like pre-images of points, I mean polyhedral map whose pre-images of points are contractible. These are, I mean, these simple homotopy equivalents are special cases. But then you sort of realize this one category. Right? This is the one category and you take the geometric realization of it. So what the geometric realization does is like you only have like sort of, you know, certain maps. Maybe in this map you only have the collapse maps. Right? Only the collapse maps have this property, and then taking a geometric realization somehow universally inverts all morphisms in a one category. Right? So it throws in the inverses, so the expansions. And I guess you can also give even more like sort of combinatorial models where you do something like finites and visual sets, where all cells are non-degenerate, and also simple maps. So in the paper there gets like a bunch of combinatorial models of what the theory of simple like finite CW complexes and simple maps is, like a classifying space. So what Hatcher does is he studies like this in families, in fibrations. So he looks at like given base space, and then he looks at like fibrations where the fibers are simple finite CW complexes and the transition maps are simple homotopy types. And then he comes up with the space. Okay, so far so good. So this is kind of my justification for this definition, which I think like isn't stated explicitly in Waldhausen-Jahn-Rockness, but this is kind of clear that this is kind of the upshot of it. That's the way we want to think about simple homotopy types. And let me say, I mean, I'm going to concentrate on these simple homotopy types, but I mean, the reason we care about those is, of course, that somehow, one of the reasons is the notion of simple equivalence plays an important role in the H-cobordism and S-cobordism theorems. Like you sort of want to decide when a cobordism is like a cylinder, and this is true precisely if the boundary inclusion is a simple homotopy equivalence. And then, I mean, what they really do in Waldhausen-Jahn-Rockness, they study like these bases of H-cobordisms. I'm not going to get into that, but this is as much as I wanted to say about why this definition is justified. Are there questions about this?
Your definition of anima simple, like what is your roads like? Did you want to do it full?
Yeah, I'd say it's a fibration, right? And the fibration is classified by this functor.
Oh, okay.
Like it's a Ricard fibration, and the Ricard fibration is classified by a map, right, into anima. I guess if you want, I can sort of say, here this is a functor into anima, and then I guess I should have, you're right, I mixed up the format. This is like what the map does, and I guess I maybe give source and target. So this is maybe into anima itself, and then you do pointed anima, like a pullback, and then the assignment will send x, z to the anima of lifts. Yes. That's the correct way. Okay, so now why do we somehow what do we want to do here? And this is kind of no, I don't have my notes, unfortunately, sorry. The point is that by definition these simple homotopy types and simple homotopy equivalence is something very combinatorial. Right? Like, and now we translate it into something which looks less combinatorial. Right? You just have an actual anima and you have a lift in K-theory. And so the main thing I wanted to get at is somehow there are these two theorems. First is due to West 77, and it says that every compact manifold, and actually more generally A and R, has the homotopy type of finite CW complex. Of a finite CW complex. And this is like topological manifolds. This is a non-trivial, I mean, it's a surprisingly non-trivial statement if you start thinking about it. Like, it sounds very innocent to begin with, but it's a surprisingly non-trivial statement. It's easy to show that it's finitely dominated. The fact that it's actually finite is like hard. And I mean, the way West does it is he uses like Hilbert cube manifolds with infinite dimensional topology. And the similar theorem, which is in some sense the Phi1 version of West, is Chapman. And this is that every homeomorphism between finite CW complexes is a simple homotopy complex. And this is highly non-trivial to think about it. Like what it says is like, you don't have any homomorphism between finite CW complexes, you have to write it as a sequence of elementary expansions and collapses. And again, I mean, this is proven using infinite dimensional topology by crossing it up with Hilbert cube manifolds, and then things become, for me, hard to follow, but the result is that. And somehow, you see, now that I sort of have translated you like sort of everything in sort of our definition, or like Walter Jan Rockner's definitions of simple anima, what you actually have to prove here, in order to prove these two results, is that you have these lifts through assembly. Right? If you have a topological manifold, you just want to produce a canonical lift through assembly. It would be a little bit more than it exists, but like you want to say it's canonical, and if it is canonical, then it's probably also invariant under homomorphism. So somehow if you combine all these results, somehow the correct statement should be every like maybe compact A and R, or every topological manifold has a preferred underlying simple homotopy type. And that's kind of what we wanted to produce, and the way we will produce this is like actually by writing down a very canonical element here, which is evidently like invariant under everything, like the right thing to do, and then you just like have to do that in a proper way, and we do this by modeling all of that by computing scale theory. And so the result we'll produce in the end is that we just have a result we produce in the end, if I find it, where I want to state it, so that I don't mess it up, is...
Thomas, can you make the mic a little bit up? Sorry.
Thanks. So we really reconstruct the functor from the one category of nice topological spaces, which are compact, and nice somehow includes A and R's. I mean, we'll see what we need as we go along somehow. My philosophy is that we just see what we need as we go along somehow. And this nice will definitely include compact A and R's, and it will include topological manifolds. It will be a little bit more general. And then you just produce a functor into, and I guess I should say, into homeomorphisms. Of course, we want a groupoid. Into the infinity groupoid of simple anima. And that will just sort of preserve the underlying anima of that nice topological space, but it will lift it to a simple anima. That's kind of going to be the result of what this will do for us, having this nice model of assembly. Okay, are there questions about this? Okay, so the main technical result will just be I give you like a nice model of assembly, and then I mean it's obvious that there are certain elements in there. Somehow, in some sense, like this is just an easy consequence once you understand the assembly map sufficiently categorical. Okay, good.
You just push up the two blackboards and...
Yeah.
How do you think of mapping spaces in this simple category?
You mean like... I guess, I mean, you can of course say what it is in terms of this assembly. I mean, you can sort of give the co-fiber of assembly a name, and then sort of express it in terms of that cofiber. But of course, if you somehow ask me how I think of that, like a priori from the definition, it's a little bit tricky. I think that's kind of the inside of Hatcher, that you can sort of come up with a space and sort of. I guess the way I think about it is similar to the way Hatcher thinks about it. You think of it like, in some sense, I think of a finite CW complex is like a thing that can be built like finitely from points. A simple homotopy equivalence is like a thing that can be witnessed finitely. Like a homotopy equivalence where you can finitely witness. So what you can think of it is like if you do delta 1, somehow you have to build up something where the total space is like itself a finite CW complex and like the map is sufficiently polyhedral. And then of course you can do this over n simplices. Just do the same thing. And then it's like in some sense a higher homotopy which is built in finitely many steps. So it's, the easiest way is to really build it as stuff over data, and that's maybe the best I can give you. Okay, so good. So how do we do this stuff? What does this has to do with the rest of my lecture? And so therefore we need to get back to continuous K theory and dualizable categories. So X is a locally compact Hausdorff space. Then, I mean, we saw that Chief's X spectra is dualizable and even locally rigid. And so we make the following definition. I think Sasha already sketched it, but let me do it again. So for C, any dualizable category, later C will be spectra, so even compactly generated. But we make this definition very generally. We define this category that I call Cauchy's head X with values in C. And what is it? It is just the inner hum, that mysterious inner hum in dualizable categories from the category of sheaves, where this just means sheaves of spectra, into C. Right, so this inner hum is a bit mysterious, but it exists, I guess. So we can make this definition, and I think Sasha sort of said he would say more about it. I hope he does. You can always model it as some sort of subcategory. Maybe let me say that it's always like a subcategory of int of like Cauchys of X. I guess, yeah.
As well as in C.
As well as in C, yes.
Which is the same as int of shifts.
Yeah. So, I mean, I think, you can. It's not so easy to say which subcategory that it has to do with this kind of stuff that Sasha will probably talk about, but it is always a subcategory of that. And somehow, what do we know about it? It's covariantly functorial in X. Covariantly functorial in proper maps. X to Y. Not in all maps. Why is that? What you have to do is you have to, the inner hom is evidently functorial in the first variable, but it's an inner hom in cat dual. So what you have to do is you have to write down a strongly left adjoint functor. Right, so strongly left adjoint functor, if I have this here, is going to be f upper star from sheaves Y into sheaves X. And for general maps, this functor is just not strongly left adjoint, right? It has a right adjoint, which is f lower star, but in general, f lower star will not have a further right adjoint. But if this map is actually proper, then the lower star agrees with the lower shriek, and that has a further right adjoint, which is upper shriek. So that's why somehow by construction, this is only covariantly functorial in proper maps. We believe it's actually functorial in all maps of topological spaces. That's kind of something I'm working on with Claudius. But immediately you get it's covariantly functorial in proper maps. And then what you can do is you can sort of make a variant of that definition, and that's Cauchys with compact support. X as well as in C, and that you can just define to be the co-limit over all compact subsets of X over Cauchy's head of K. Right, if your spaces are nice, have enough compact subspaces, then you can make this definition. And this is actually covariantly functorial in all maps. Functorial in all maps. Right, why is that? Because, obviously, this construction is covariantly functorial in all maps between compact spaces, because every map between compact author spaces is like proper, and here you just reduce it to like looking at the induced maps between compact subspaces. So that's like, and this is like, in some sense you think of this as having compact support. We'll see why we do that in a second. And let me give you one remark. I mean, I guess, in some sense, the cool thing about this whole stuff is like, once you know enough about dualizable categories, you don't need to worry about the fact that you don't understand this category. You just need to follow one fact about it, namely that we understand its compact objects. So what are compact objects? Right, so in general, in the dualizable category, compact objects are just maps of dualizable categories, in other words, strongly left adjoint functors, from the category spectra into your given, like, sorry, I should not forget the head, into your given category. Right, that's just generally true that compact objects are the same as strongly left adjoint functors from spectra. Right, a functor from spectra, if its left adjoint determines an object, and it's strongly left adjoint if and only if this object is compact. But then you can sort of play around, and this was by definition the inner home, and you can just use the definition of an inner home that you can bring the source over here, right? If you map into an inner home, by definition, this is the same as strongly left adjoint functors from sheaves, as well as into C. Right, in this category we fortunately looked at the other day, in my very first lecture. What is this category? This is somehow just the category of, or the full subcategory of the category of co-sheaves on X as well as in C. And it's full on those co-sheaves F, which have the property that F of U to F of B is compact for U deep inside of V. Right? Maybe I should sort of say here, full on. Right, so this is a very concrete description of a category. So these compact objects. And in general, I mean, this category has a lot of objects which we don't really understand, but these ones we do. Okay, so that's the one thing I want to say about this category, I guess. And now you need to, we want to understand the K-theory of this category. And here's the proposition. And remember, I mean, Sasha talked about how one contributes a K-theory of these inner homes under assumptions on the source. And the assumptions on the source were that source was proper and it was countable at infinity, or in other words, the co-evaluation was an omega-1 compact object. And this actually turned out to be the case here. So, and I will need, this is the first place where I need niceness assumptions on my space X, and let me maybe sort of make the assumption that will just work throughout, and then, I mean, I'm happy to discuss. I mean, I'm not sure how happy I am. We can discuss how to do that. Let's get into the realm of concept topology, of course. So let's assume that the topos sheaves X as well as an anima is of locally constant shape. I mean, e.g. if X is alpha complete and locally contractible, sublocally contractible, or if it's an A and R, something like that, this will be satisfied. So yeah, I will say in a second what this condition gives us. So basically, this condition is equivalent to requiring that the functor, which is for this topos, for this topos you always have the geometric morphism to the point, right? So in this in particular gives you a left adjoint morphism from anima into that, which is maybe the upper star of the morphism from the point, and so this actually implies that this has a further left adjoint, P lower natural. Right, so this is somehow the condition that we write is actually equivalent to this requirement that this further left adjoint exists. And I mean, we know this already has a right adjoint, so somehow, already this looks good. We have a triple adjunction, things start to look okay. So that's an assumption I will make. And so then the statement is then co-sheaf set X with values in spectra, say, I guess I could say this was in T, but let's say spectra, is proper. If X is countable at infinity, then it is omega 1 compact. Countable at infinity means sigma compact. I have an exhaustion by like compact sets.
I'm sorry, weren't such as like statements about the humps about the first variables or sheaves rather than the dual itself?
Oh yeah, yes, absolutely. Sorry.
Yeah.
Yes, sorry. Yeah, absolutely. Yeah. I want to make a statement about the first variable that induced that the home computes the correct thing, and let me maybe just say one word about the proof because I think it's kind of instructive to see where this condition enters. So what we do is we look at. I mean, what we have to do is we have to look at the evaluation. Sheaf spectra, tensor, sheaf spectra. And then we evaluate down to spectra. And how was this evaluation defined? This is kind of why we went through this whole locally rigid stuff. So the self-duality, the evaluation was defined to go, we first have the tensor product, the spectra, right? The tensor product was the same as the upper star. And that we already saw is like strongly left adjoint. And then the second thing you do is you just do the upper star functor down to spectra. So now if you want to prove this composite is strongly left adjoint, you check that both of these, this is already strongly left adjoint, so you exactly mean that this is
Lower
strongly.
P lower shriek.
P lower 3, yes, thanks. Yes, thank you. P lower shriek is the functor here, right? That kind of, I messed up my own discussion, but I discussed it at length yesterday or somehow. This is the co-unit of my locally rigid, my Frobenius algebra. And so you want to check that this is like, wait, sorry, I lost a little bit. I want to say this is strongly continuous. So, in other words, the upper shriek has a further right adjoint, right? The upper shriek is by definition the adjoint here, and you want to check this has a further adjoint. But now the point is that we saw actually that the P lower shriek is dual to the functor P upper star. Right, that was kind of the thing I said, like under Verdier duality, this adjunction lower shriek, upper shriek corresponds to the upper star, lower star adjunction. And now if you think about like duality, if you want to check that this functor P lower shriek is strongly left adjoint, you have to verify that this has a further left adjoint. So that's a little bit confusing, but why is that? Because if this is like strongly continuous, you have a further right adjoint in PRL, and then you dualize this adjunction, and so the further right adjoint in PRL comes over to give you a left adjoint to this. So my claim is that this is exactly like strongly continuous if P upper star admits the left adjoint. And that's kind of the assumption we make. And there you see, I mean, what we really need is not quite that this is unstably true, but you only need it stably. So I guess you could sort of replace this assumption by stably locally constant shape, or stably locally contractible. Okay, so that's kind of what we need here, and I guess I didn't want to say much more about that. Yeah. Okay, so this is what we need for this category to be proper. And what is a corollary? Corollary, under these assumptions, we have that what is continuous category of this category Cauchy set X is less than C. Now we know from Sasha's general result that we can compute this as, I guess, what I would call a KK, continuous KK theory, from sheaves X into C, which I just mean the map in non-commutative motives. By definition, this is like the mapping spectrum in motives from, I guess what Sasha called U of sheaves X into U of C. Right, this is what the result gives us. But now the point is that this motive of sheaves, we understand. Like if X is compact, this is basically a mapping spectrum from X into spectra. And so what you're doing is you just, I mean for X compact, it just takes a dual basically, so you map into C. from a mapping spectrum, and that's just the, that's cohomology, so the dual would be homology for X finite. And in general, it's locally finite cohomology. So if you think about this for a second, like, let me not go through this here. So what you get is actually that this whole thing is equivalent to the locally finite homology of X with values in continuous K-theory of C, and I guess Borel-Moore homology. So I guess one way to say what Borel-Moore homology is, it's like P lower star, P upper shriek of K count of C. You want to use like fixed.
Can you click on the thing? Sorry, it's a.
And I guess, for example, if X is compact, which is the case we will care about, this is basically given by tendoring with the homotopy type of X. X tendor K continuous C. Where, I mean, pi infinity is the shape of X. Whatever. If the space has locally singular shape, this is just sign of X. In general, it is the shape. This is actually, I guess, the finite anima. If X is compact and locally of constant shape, I think this is shown by Marco Volpe in one of his papers. This is like finite anima. So this is what we get. We get the homology, the K-cont homology of that finite anima. And yes, that's maybe the result. And I should say, the result is also true, like if you don't want to get locally finite homology, but just homology, which is like just P lower shriek of P upper shriek, then you have to use this category of co-sheaves with constant support. Right? Because it is true on compacts, and then you sort of apply the result on compacts and write the whole thing as a polynomial of those. So that's somehow like, if you want actual homology and you don't want to make compactness assumptions as opposed to Borel-Moore homology, you need this category of co-sheaves with compact support. Okay, are there questions until here?
Any of these assumptions is also assuming countable at infinity, or just assuming?
No, also countable at infinity. I guess somehow. I mean, as I say, I will care about the compact case, but in general, otherwise this category is not omega 1 compact, and then I think Sasha tells me the result is probably false. I haven't seen a counterexample. Who knows? Like that. Okay, good. Okay, so now what is the point? Now we have this nice category, I mean somewhat nice category, Cauchy's set, and its K-theory is K-homology. And so here's the top proposition that, I mean, there's a canonical compact object, canonical compact object, chi log, in the category of Cauchy's head, X as well as in C. I should get back from. Under the same assumptions, like the local niceness assumptions on X. So the topos has locally constant shape. We have this object. And I mean, canonical means like, it is very easy to write down. What is it? I mean, there's a bunch of equivalent descriptions of this object, but so one description is, I mean, by the assumptions, we just have this functor P lower sharp, natural, from sheaves X spectra into spectra. And by definition, it came as a left adjoint to a functor which already had a right adjoint. So this is a strongly continuous functor, and so there we saw like that. These are, I mean, compact objects are just these strongly continuous functors. We can also somehow, by the fact that this is locally rigid, we know every continuous functor has to be of the form P lower shriek of something tensor, I mean blank tensor something. You can work out what that something is, and the claim is a dualizing complex. So under Verrier duality, it sort of corresponds to the most canonical object you can think of, namely the dualizing complex. And maybe, I mean, there's also a very concrete description. I told you that these like compact objects are in particular like co-sheaves. What is the co-sheaf? You can just take the co-sheaf, which assigns to every open U you know, a co-sheaf has assigned a spectrum to every open. What you do is you just take the suspension spectrum. So that is maybe the most canonical co-sheaf you can think of. It's just somehow, in some sense, the identity co-sheaf. Send every open to itself. And so this is kind of the description of this object. And part of the claim is, of course, now that sort of under this niceness assumptions on the space, this co-sheaf satisfies the condition that whenever U into V is like deep inside, then this induced map has finite rank. Because this is what compact Morphin spectra are. Okay, so I hope you agree. I mean, if you like one of these three perspectives, that this is like the most canonical object that can exist in this category. Okay.
And was it so now was this in the early proof? Could you sort of figure out? Could you sort of like dig out that class? Is that, you know?
I cannot. I mean, it's a good question. So I think Jesper's question is like whether now if we go back and claim this is a class which we somehow get out of this infinite dimensional topology stuff, can we identify that actual lift with the lift here? And no, I certainly can't. I mean, there are like more modern proofs. Maybe I should have meant that there are more modern proofs by Peterson-Weibel and Vanitsky-Yamaguchi, where they also already use something like controlled algebra. And I don't think they compare their list somehow to the original ones. But I mean, I think it's at least like thinkable to compare our class to theirs. I have no clue how to compare it to this infinite dimensional topology class. Yeah. Okay, so anyways, this is a class, and so as a corollary, we get a class pi log, a class in this K-theory for X compact. I mean, I guess in general, it's true that we get a class in Borel Moore homology, but let's say for X compact, we get a class in this pi infinity X kind of head-count of spectra. Okay, so say like that, which is K of the sphere, A of the point. But that's kind of the class we get, and let me actually mention that I personally find continuous K-theory somewhat mysterious. Like, we don't know much about it, right? In general, somehow, how do we even write down classes, like, in continuous K-theory? Like, somehow the only mechanism we somehow know, I know, like, to write down classes in K not continuous, which is not opaque, is to actually sort of take a compact object.
Oh, I know another one.
Yeah. I mean, I guess you read it as a project. I guess maybe we can answer this question, but what I want to say is, like, in the category of sheaves, right, there is just no compact object. Sasha proved that for us yesterday, like, in reasonable cases. Somehow one of the advantages of this category of co-sheaves is that it actually has compact object that gives rise to interesting classes. And, I mean, maybe I should sort of ask this as a question. Maybe potentially Sasha has an answer, but in general, I'd like to know what... Is there a good, useful description? I mean, a nice, say, whatever this means, description of K naught continuous of any category, right?
I mean, I don't know how nice it is, but it's the same as usual K0 of the fiber product.
Yes. Okay. So I guess somehow one way is to say it's K0 of this fiber product of int C omega 1 over...
Just C omega 1.
Yeah, okay, yeah, right. So int C omega 1 over calc cont C with C omega 1. So in other words, you manage to write down objects in here, then somehow this gives you classes. Okay, anyways. Okay, so I think this is, I mean, I personally think this is an interesting question whether they can do that. I mean, in principle, we can also give like other descriptions of like continuous K-naught. It would be nice to have one. But okay, here we don't care. We have enough compact objects. They give us the classes we want. Okay.
Thomas, could you try to repeat just the assumptions on X? So
at the moment, the assumptions on X are literally just that X has locally constant shape. The locally compact Hausdorff space which has locally constant shape. That is, and somehow this is even too strong. What I really need is, like we say this, we really need is X is a locally compact Hausdorff space, and X has stably locally constant shape.
course actually need to be compact.
Yeah, I guess it is true because, I mean, but it's only true, I mean, you don't really need it. It's only true because I wrote the right-hand side I wrote. Otherwise, you would write the Borel Moore homology and you always get this class kind of. Yes.
Sigma compact.
Ah, yeah, right, sigma compact. Okay, so, yes, sigma compact. Countable edge infinity. Sorry, I forgot about that. But these are all the assumptions, and as I say, like stably locally constant J basically means that this lower sharp exists stably. And in practice, you can sort of wonder whether you can give efficient ways of like determining that this is true, and one can. But I don't want to get into this points and stuff here. Okay, cool. So now what? Now we have this class, and of course, in order to do what I want to do, I have to prove that this class, which I produced here now, lived somehow the class I started with, the Euler characteristic. So I have to sort of relate it to something I know under assembly. And that's maybe the main point of what we do. Namely, write down a functor that models assembly. And then you literally just see that this class just goes to the class which models the Euler characteristic, which is just a constant sphere. That is what I do with Arthur Bartels. The following result, I mean, there is a strongly continuous functor. And again, I'm going to keep those assumptions like my standing assumptions for the moment. I'm happy to talk you through the functor and we see where we need it. But the claim is that there is a strongly continuous functor A from this category of Cauchy's hat X with wells in C into C to the pi infinity X. C to the pi infinity X is just a functor category. I mean, I guess it's equivalent to the category of local systems on C.
On X.
On X, yes. Local systems on X with values in C. Yes. This is also like somehow under the assumptions that my topos is locally nice. Otherwise, I mean, there are things you can write here and if you're not in this situation, but let me stick to it now. And with the following properties. First property is it induces the assembly map on K-theory I guess I should say, okay, so now there are two choices I can make. Either I can just say compact support here, then it's just true without assuming X is compact, and then you have this map, and it generally gives you the assembly map on K-theory. And the second assumption is it takes chi log to chi. Chi, which was a class of the constant sphere for X compact. X compact and C being spectral.
But 2 is already tried the level of categories, right?
Pardon me?
2 is already tried the level of categories, it's not only a K-theory statement.
Yes, I think this is what I wanted to, like I said, I shouldn't write class, I should write what's the name, sphere. The constant sphere. So the most canonical local system you have on X is just
the zero local system?
Hmm?
The zero local system?
Thanks. The other valuable comments. Okay, so good. Okay, so let me indicate how to do this. Proof/construction. I mean, in some sense, this is really a construction, maybe rather than a theorem. Like it is write down this functor and then it does what you claim it does. And I do it for X compact. Right, so what am I doing? So Cauchy's hat was in C was just by definition the inner Hom from sheaves X into C. And so what I can do is I can just tensor this whole thing with spectra to the pi infinity X. Right, so then I get something in Hom from sheaves X, tensor spectra to the pi infinity X into C to the pi infinity X. And now what I'm doing is I'm going to pull back in the first variable along something that we call the diagonal class. And that will sort of, I tell you what the diagonal class is in a second. So this will get me to the inner Hom from spectra into C to the pi infinity X. And that is just C to the pi infinity X. Okay, so this is what we want to do. And obviously, I mean, this is a strongly continuous functor, and this will be pullback along strongly continuous functor.
Go ahead, sorry.
Ah, okay. So D is going to be a class.
So the internal Homs are all dualizable.
The internal Homs are all internal dualizable inner Homs. Yes, thanks. Okay, so, and by the way, I mean, this description of the assembly map is highly inspired by like Baum-Con stuff, like somehow. If you think about like how people in Baum-Con write down the assembly map, this is exactly how they do it somehow. I mean, there's a meta project here going on, which is like, say, assembly in Ferrell Jones as close to Baum-Con as you can. That's maybe the meta project we're running here, but let me just tell you what the diagonal class is. So this is a strongly continuous functor from spectra into sheaves X tensor spectra to the pi infinity X. So in other words, a compact object in this category. And I want to think of this category as like, I mean, sitting inside of, I guess what I'm doing is, it's left adjoint, so this functor is left adjoint to the functor which is, I guess, one way to say it, sheaves X tensor local systems. Sorry, what? Did I mess up the directions here? No, it's correct. So I want to go here, and then you can sort of embed local systems into sheaves. Psi upper star. So by definition, local systems are a full subcategory of sheaves. And then you have this, and then you can do like a sort of diagonal pullback. Right, and then I guess here you can, I guess here's an object. So what you do is I guess you could even go further down the spectrum. And I guess in other words, what I'm saying is I'm claiming that this functor admits a left adjoint. This composite here admits a left adjoint. And then what you do is you apply this to the sphere. In other words, you sort of try to push forward, but you lower natural want to push forward the sphere to a diagonal class. You can't, because the lower star, the lower natural doesn't exist for the diagonal. The claim is if you further sort of make it a local system, sort of commodify in one variable, then this functor exists. And so somehow I'm using some implicit claim here, but sort of morally you want to think of this as a diagonal class. But it's kind of the lower natural along the diagonal, except in one variable you also have to consider it as a local system. That's what this class is. And again, by construction, this is going to be strongly left adjoint because these functors both have right adjoints. And then it's going to be strongly left adjoint, and then apply it to a functor from spectra into sheaves on X, which is like, by the assumption that X is compact, the sphere is a compact object from sheaves on X. Yes?
Now I have is it the same thing as just recomposition with the map local systems for sheaves by pullback? Like, looks formally as if you are just pulling back the local systems and then just quickly identify local systems with the tool.
I don't think so. Like, sorry, what are you suggesting? I'm doing.
There is this like better version of this shape functor of many local systems.
Yes, okay.
Then
Yes.
I thought like the natural thing to do, try to recompose with it, but maybe I just get it wrong.
I don't think it's that, but let's discuss this afterwards. It could be. If I understand correctly what you say. Let's discuss it afterwards. I don't think so, but let's see. But anyways, this is kind of the description we have. And now, maybe, I guess I'm basically out of time, so let me just say that, because I want to write down one more result in the end, is that somehow, I mean, now the Chi-log had a very canonical description, right? Sort of, we just sort of, what we have to do is now we have to take Chi-log as an object in here for C equals spectra and just chase it through this functor. You can, I mean, it's not so hard to actually do it, because somehow what you can do is you can pretend these functors have like left adjoints, which they don't, but if you pass the pro categories, they do, and then it's basically just composing of left adjoints, because the kind of class, the Chi-log, was also like a left adjoint, like P lower natural. And then, I mean, it's very easy. And yeah, okay, so this is kind of my proof sketch. And so you see here, we have a very, very general result. Maybe, I guess I don't have time to talk about more stuff. There's a very general result here, and that's maybe the main theorem, as I say. Like, the main theorem is that there is a very general model of assembly maps, and it's only this kind of geometric, this application, the simple homotopy type is just one application you can do, because you have this canonical map. Of course, the real result, I think I also said this at ELJS a year ago, that the real result here is this description of assembly maps. And the real version of assembly maps, somehow, there's a lot of work to do here. Because what you really need, sort of in more geometric applications, is versions of assembly maps which see some equivariance, and you want to apply it to some sort of classifying space and stuff. So you somehow need to play around with assembly, but I'm somehow positive about that, because somehow this is also canonical and straightforward, that it's in some sense clear that, and you can work it out, we have worked it out, that there's many like sort of ramifications of that idea that still work. Okay, and then, I mean, thanks very much.